All right. Well, and again, if this does not work for some reason, please let me know. But at the end of 2.3, there's a topic called the squeeze theorem. And you know, our goal here is to be able to calculate limits, right? We're trying to find limits, and we have a couple different strategies, right? So I guess before I dive into the squeeze theorem, remember a couple of our strategies. Number one is we have these infinite limits, and we have an infinite limit whenever we're looking at the limit of typically it comes at the moment from a rational function, f of x over g of x. We have an infinite limit when the bottom function is going to 0 and the top function is not going to 0, right? So that's one strategy to look for, right, is infinite limits. We also have this method called direct substitution. That should be your very favorite method of all of these, right? Direct substitution, at the moment, we know it works for polynomials and rational functions. And that's where the limit as x goes to a of f of x is just equal to f of a, right? And I've said a number of times that's not necessarily true, right? But for certain types of functions, and it turns out actually quite a few functions, that is true. The limit is equal to the function value. And that's really when we have a situation, you know, where the function is just a nice function like that. The function value and the limit are both going to be the same in that case. At the end of our last section, and hopefully as you were working through the homework, we had what I call these indeterminate forms, right? So indeterminate forms is when we, again, typically it comes from a rational setup, f of x over g of x, and it's where both the top and the bottom are both going to 0. Right? And that's indeterminate. We don't know what that is going to be, and this is where we have some algebraic steps. So we want to use algebra to, I'm going to say simplify, although I'm putting that in quotes because the goal isn't always really to simplify it, but it's to cancel out that common factor, that 0 over 0. So you would have seen some with factoring, you would have seen some with fractions, would have seen some with the conjugate. Okay. So these are all useful strategies, and there are ones that we like to employ, but there are certainly situations where none of these strategies work. And here's an example of one of those. Let's look at the limit as x goes to 0 of x squared times the sine of 1 over x. Okay, and as before, don't feel shy about jumping in and interrupting or chiming in with a question. The goal is not for me to speak freely, right, but to have you guys learn, right? So jump in. So this is a limit that we're trying to find. You may remember a little bit of those limit laws that said, well, I can take each of these limits separately, right? That was one of our kind of limit laws. If I have the product of two functions, I can take each of those limits. This limit is definitely going to 0. This sine of 1 over x, however, you might recognize that one. That's this function that goes and oscillates kind of rapidly right around 0, and it turns out that limit does not exist on its own. So because of that, we can't use no limit laws. Can't use the limit laws if you have a limit that doesn't exist, right? Sort of all bets are off if the limit doesn't exist. You might, when you combine them together, you might get a value that exists or it might not exist, but you can't add or subtract it because it's not even a value that exists, okay? So be careful of that, and that's also true, of course, for infinite limits, right? When you have a limit that is infinite, that doesn't exist, and so you can't add or subtract those in the standard way. They're not numbers, right? You can't add or subtract them. So we're a little bit stuck here. It's not a polynomial or rational function, so direct substitution isn't going to work, and it's undefined there anyway because of the 1 over 0. It's not really this indeterminate form. We're sort of stuck. Now, if we had used the suggestion earlier and we said, I don't know what to do, so I got to try something, you could certainly start to plug in some numbers and see what happens, right? You could pick some values that are very close to 0 on either side. And what you'd find is that the x squared is still going to 0, and the sign of x sort of bounces around because it's going to be sometimes positive and sometimes negative. But you might remember the sign function, no matter what I put into it, the sign is never bigger than 1 or less than -1, right? It's always between 1 and -1. So I'm multiplying something that's at most 1 by x squared, which is getting really, really, really close to 0. So when I multiply this together, you might intuitively begin to guess that it actually is heading towards 0. Right? Now, that's really a guess, and maybe by plugging in some numbers, we'd also get that guess, right? And guesses are useful, but of course not something we want to count on, right? So what we need is a proof or a strategy, and the squeeze theorem, it turns out, is that strategy. So here's what the squeeze theorem says. Squeeze theorem. It's also called the sandwich theorem, or I'm sure it's got other names too. A little bigger here for you guys. So the squeeze theorem. It says if f of x is trapped between g of x and h of x for all x not equal to a in an interval containing a. And just in case you're rapidly copying all this down, I will scan this and post this to D2L just like I did with the other lectures, and I'm recording this, so I'll put that in D2L too. So, you know, take notes if that helps you concentrate, but feel free to just, if it's possible, to kind of focus on it as well, and that sometimes is a good strategy. You don't need to copy down everything that I say. Okay, so if we have this function f of x that's trapped between this h of x and g of x, everywhere right around a, doesn't happen to be at a, and if the limit as x goes to a of f of x, or sorry, it's not supposed to be f of x, h of x, equals the limit as x goes to a of g of x. So the two functions that f is trapped between, if both of their limits are going towards the same thing, call that L, then, this is the conclusion part, if you can show all of that is true, then you know the limit as x goes to a of f of x also has to equal L. That's called the squeeze or the sandwich theorem. And visually, you have this situation. You have some potentially crazy function f that we don't quite know how to deal with. But if we can trap it between two other functions, and both of those other functions go towards L, then our function also has to have a limit of L. If those two functions have a little space between them, then who knows, the limit may or may not exist. But if they both go tight to L, they're equal to L, then our function also has that limit. So this is a strategy that we use. Now in practice, it is a little challenging to actually apply. And that's because it's hard to figure out this h of x and this g of x unless you have some spark of creativity or intuition for a particular problem. It's hard to kind of figure out how to bound the function that you care about, right? This is the function we're sort of interested in. In order for this squeeze theorem to work, I really have to kind of have an idea already what the limit should be, and then hope that I can find two functions that satisfy these requirements. Okay. Here's our limit. You might remember that I already kind of gave you almost the bounds of this function. The sine function is always less than or equal to 1 and bigger than or equal to -1, right? That's a fact that I mentioned. Now that's not quite the function we're interested in, but if I multiply this function on all sides, or this inequality on all sides, by x squared, what I get is this inequality, right? This top one's true. X squared is a positive number, so I can multiply all the way through, and this second inequality is also true. And this is almost exactly, well, I'd argue it is exactly what we want. I have my function, x squared sine of 1 over x, and it's bounded by these two other functions. Notice, as x goes to 0 of minus x squared, that's just a polynomial, so I can use direct substitution there. If I put in 0, I get 0 squared, which is 0. If I look at my other function, same approach, right? These two facts together, the fact that my function is bounded by both of those and that both of those are going to 0, those are the conditions for the squeeze theorem. Since I met both of those conditions, that gives me the conclusion. The conclusion is that the limit of my bounded function, sorry, that's not right, the limit of x squared sine of 1 over x, that was my bounded function, is also equal to 0. In practice, like I said, it is hard to come up with those functions for just some arbitrary tricky function. So you won't use the squeeze theorem directly very often. You'll be prompted, I should say, to use the squeeze theorem. So if you're just asked to find a limit, I wouldn't, in general, expect that you would use the squeeze theorem, right? So I would say something about using the squeeze theorem, or I would give you some bounded functions or some things like that to give you a clue about how to approach that problem. Questions? Any questions on the squeeze theorem?
So this particular question was pretty easy, but they're not always going to be like this, right?
Well, no. But I will say for this, well, for the squeeze theorem, they kind of will be, I would argue. So like I was saying, I can't just ask you or make up some kind of crazy function like this and expect that you guys are going to be able to come up with these sort of bounding functions. Now, once you've seen this, I could give you, a really similar type of limit and expect that you could kind of duplicate that strategy. X to the 4th times sine of 1 over x, or x squared times cosine of 1 over x, right? Those are basically the same problems. But another strategy I can do is I can say, I'll give you a complicated function and I'll say, here's a function that's less than it, and here's a function that's bigger than it. What's the limit as that function goes to 2?
Okay.
So then you would say, okay, well, I've already got the bounding functions. Let's just show that those limits both go to the same value. Then I know that my function goes to the same value.
Okay, so it's all about finding those h of x and g of x.
It really is. And it's not like they don't just like kind of appear.
Yeah.
You're doing it because I kind of know what the limit is already, right? Like I'm just proving that it really is that value. So like this one, I kind of know from thinking about it. Well, I know it because I've done this one a bunch, right? But I would also maybe be able to see by thinking about it that these quantities are going to go to 0. So then I'm thinking, is there some way that I can find two functions that are also both going to 0? And even then, it takes a little bit of luck to get there. Right? So it's a good thing to see because I think it helps illustrate how finding limits is a little bit of an art form. It's not just a procedural, like solving an equation is kind of like a procedure, right? You just do the right steps and don't make a mistake and you get the right answer. But limits sometimes have to be creative to figure out how they fit together, okay? And that's a change from probably most of the work you guys have seen in the past. But it's not, you shouldn't feel intimidated by the squeeze theorem just because the kinds of questions that I'm able to ask, I have to really give you a big clue that it is a squeeze theorem. So yes and no, I guess, to your question. They're certainly not always quite like this, but my expectations are pretty straightforward for these.
Okay, thanks.
Yeah, good question. You guys have been in enough math classes, you know how that works, right? The teacher always shows some easy examples and you guys feel good, and then you go home to your homework and you realize they're not always quite so easy. But as a math teacher, it's like the idea is the same, right? So like I think sometimes in our brains we think, well, it's the same idea, but of course it takes a little bit to see that idea, right? When you're just learning it, when it's your first time through. Okay, anything else? Okay. All right, so it's fun. So 2.4 is it's introducing something called the precise definition of the limit. And maybe I've done too much hinting, right? But I've kind of hinted at our definition of the limit as being a bit substandard, right? It's like as close as we want, and this kind of casual terminology for something that is, the building blocks of this whole course and a really fundamental idea in human history, right? So there is a more precise definition of the limit, and I want to introduce that and talk about that today. We don't cover 2.4, I don't cover 2.4 in detail with my classes. There's some proofs in there that we actually had a spirited discussion in the department over whether we do the proofs or don't do the proofs. So if you took this course from a different instructor, they might have you go through the proofs. I sort of just skim the surface of those. If you're planning on going on in math, I would encourage you to really look a little more deeply at the proofs. But for the rest of us, it's fine to just have an understanding of what this actual definition is. So we know the sort of intuitive idea of what the limit is, right? And we're already able to find some limits. but we really, some of those rules and properties are actually based on this precise definition. So I'm going to write it down, and then I'm going to break it down for you, and then I will show you some pictures and maybe even a little applet to all help us kind of get the feel, terminology for the way of talking about our idea. And it's really important because if you don't have a vocabulary like mathematical terms, you can't think carefully about those ideas either, right? That's true in every field, not just math, right? Like you can't do biology without having your vocabulary, right, from like anatomy and physiology or whatever those courses are, right? They just cram a whole bunch of terms, but those terms are really important because they help you see the body in a different way, right? And so don't discount the power of vocabulary, right? It's a way that we have of expressing our ideas. If you don't have a very adequate vocabulary, you have fuzzy ideas, right? And that's not okay in a math class. So, precise definition of the limit. It says, for every epsilon bigger than 0, so that's a Greek letter, my version, right, of the Greek letter epsilon. So think of this as like a really small number. So for every small number that's positive, there exists a delta bigger than 0. These are lowercase Greek letters, such that if, give myself a little more space, if x minus a, oh, I guess, sorry, it's kind of a hasty start here. What I'm defining is our statement. I'm saying the limit as x goes to a of f of x equals L. That statement means this, right? So when we write that, when we say the limit is a number, what we really mean is this. What we mean is that for every epsilon, there exists a delta such that if x minus a is less than delta but bigger than 0, the absolute value is distance. So we'll talk about this. So if this is true, then f of x minus L is less than epsilon. And, you know, that's, well, I don't know that that makes any sense to any one of you, right? That's kind of crazy talk. What does all of this mean, right? So let's break it down in terms of what we already know about the limit. So we know that a is this x value here, and that L is the limit. Right, this is our function f of x. Okay. And so what's all this business? This, for every epsilon bigger than 0, is really representing like a distance that the function values are from L. So these absolute values are saying distance. F of x minus L is the difference or distance between the function and this limit. And we're saying that that is less than epsilon. So I could go L plus epsilon, or I could go down to L minus epsilon, right? And any value in this region would be like in my target area. So what this definition says is that for every epsilon bigger than 0, so I picked, you know, this epsilon, this distance, so that we could see it, but that epsilon could be as small as you want, right? You could have it a billionth of an inch, and you could cut that into a billionth. You could make it as small as you want. If for every epsilon, no matter how small you make it, there is a delta. So a delta is a little region, defines a little region around a, the x values. So a plus delta and a minus delta. So this is saying that if x minus a, the distance between an x minus and an a is less than delta. So that's saying I can pick any x in this region, but notice it has to be bigger than 0. So that means I can't actually pick a, right? And we know that from limits. It doesn't matter what a is, so I don't want to consider x equal a. So any other x in here, if x is within delta of a, so that just means like in this little neighborhood, then the corresponding function values need to be within epsilon of L. So each of these x's here has a corresponding function value. I've tried to draw it in a way that each of these x's, their corresponding function values all fall inside this epsilon target, this distance around L. If I can do that, if I can find the right region around A for every single epsilon you pick, then I get to say the limit of the function is L. If there's some epsilon where I can't do that, then the limit is not L. The limit is something else or doesn't exist. And that scenario would look like this. I think you can see here that if my epsilon neighborhood, think of that as like a target around L, is that small or smaller, it could be smaller than that, right? This is just so we can see it. No matter how small I pick my region around A, any x value that falls over here is going to fall, the function value is going to be up here, which is bad, right? That's not in my neighborhood. That's not what I want. So for this, I don't get to say the limit is L because there are certain epsilons where I'm not able to find a delta. I just can't do it. No matter how small I make my delta, it's never going to work. Okay. So this terminology is a mathematical expression of that idea of what a limit is. And it is important to me that you understand the terminology. So I won't ask you to memorize the definition. Sometimes I have, but I'm feeling generous. It's the pandemic. No, I haven't done that actually in a little while, make you memorize it. But I will ask you some questions involving deltas and epsilons. And what's critical there is that you understand that delta is the region around A, and epsilon is the region around L, and that those targets sort of have to match up. Okay. Let me show you, if I can here, a little applet of this. If I can find it. This one's probably best. Yeah, so there's kind of a question about, there is a structure there in terms of epsilon and delta, and the delta depends on the epsilon. So you're not going to be able to find a delta that works for every epsilon, right? Because as soon as you lock a delta, you can just like shrink that epsilon down. The game is that you start with an epsilon, and then you can adjust your delta to make it work. So the deltas depend on what the epsilons are. Okay, let's see, where is it here? Okay, so this is off of Desmos, which is a really nice web-based graphing tool. It's what I use a lot if I have to graph something. I don't actually have a graphing calculator here at home with me. So I just use Desmos, and it's nice. If you haven't used it before, it's kind of a, it graphs the way you'd kind of like things to graph, I find. So this is kind of the scenario. This is how it came. So the function they're working with is this 1/6 x squared, which is this black line. And then they've set up these kind of regions. This blue region is there. What they have written is actually equivalent to what I did with the absolute value in our definition. The y values are between f of a minus epsilon, capital E is what they're using for their epsilon, right? Minus E and plus E. And then it's the same idea here for the x values, the region around that. So this is picking where that A is. So it doesn't matter so much there. A is equal to 3. So the idea is that if I pick an epsilon right here, let's say 0.25, the current delta or D does not work, right? Because there's all these values up here, right? Anything in the orange is fair game because that's within delta of 3. And a number of those function values fall outside of that blue target. But that's fine. I can shrink that delta down so that it matches. This looks good. It appears to me that every, and zoom in a little, that every every x value from the orange corresponds to a y value that is inside the blue target. It does not have to be exact, but I cannot go over, right? It's okay if it's a little bit too close together, typically, like that still works. That delta works and that delta works, right? Oftentimes the question will ask you something about what's the smallest delta, but theoretically, all of those delta values work. Okay. So then the game would be, okay, someone picks a smaller epsilon. Can I still find a small enough delta? And it appears I can, although I'm starting to run out of graphic space there. Okay. So it's like a little visual representation of what's going on. I don't know that it's revolutionary, but it is illustrating the idea. There are lots of other versions that are very similar ideas. Okay. So you'll see some problems where they show you a sort of picture or image, and you may have to figure out what is the delta and what is the epsilon for that particular scenario. One thing that does come up, and I think I'll just show this on the overhead camera. One thing that will come up is that you, depending on what your graph looks like, it's kind of a little ugly, but let's call this A. It's not always symmetric. Like the epsilons defined a symmetric region around L, same above and below, but the sort of corresponding endpoints, notice here, are not symmetric around A. This might be, you know, A minus 0.1, and maybe this value up here is A plus 0.2. Right, this is like twice as big as that region. So the question then is, what is our delta? Delta defines a symmetric region around A. You always want to pick the smaller delta, right? Because it's okay to be a little bit too small or have some values that are too far inside, but it's not okay to be too big. So if I pick delta to be 0.2, that would fail for this epsilon, because 0.2 would allow me some x values out here that would fall outside of my region. Okay, so in this scenario, your delta would be 0.1. And so if you have two options there, you want to choose the smaller of those two options. Okay. See, now if I were in class, I'd be able to look at you all and see your glazed over faces and reassure you that it's okay. Here I just see a bunch of names, so I don't know quite your reactions, but it's a subtle idea, but it's mostly just terminology. It's really just a way of formalizing what we had already talked about last week, right? With the idea of making the function values close to this certain thing. That's what the limit means. So now we just have a formal definition for that. And from that formal definition, you can actually prove some of those limit laws and rules that we were using earlier. And that's, of course, very important to mathematicians, that everything is 100% on a firm footing, right? Because, well, I guess if you're in physics, you know, and you assume something's true and you go off in some wrong direction, eventually you're going to bump into something that doesn't work, right? It's like, okay, well, that must be wrong, because, you know, gravity doesn't work that way. But in math, because we are sort of an exercise of the mind, if you have a hole, you may not really discover that until I don't know when, right? So we need to make sure that at every step that we are convinced, or at least shown why each of those next steps are true. And that's actually a really nice thing about calculus and teaching calculus, is that while it's a really big idea, it's organized in a way that we can show you everything, and you guys really can understand everything, or 95% of everything, of why it is true. You won't learn it all because it's complicated, right? I've been teaching it a number of years, and I still learn things every time I teach it. So it's a rich subject, but you will have seen basically all of those ideas when you get to the end. So there's very little that I have to say, trust me on, right? Which is really nice for me, because all the other courses we have to say, well, just trust me, it's true, right? You might see it later. This is just how we do it. But I don't have to do that in calculus. Almost, it's only one or two things that we have to do that are very minor. So it's a great topic, but this delta epsilon, or precise definition limit, is an important idea. So again, you won't have a ton of questions about those, but understand what those pieces mean. Okay. Any other kind of questions about the topics or the material there? So again, just as a reminder, make sure that you are keeping up with your take-home work that's due this week, as well as your homework assignments that are due. And as we've talked about in the beginning, it's really best if you can do a little bit at a time, right? I mean, even if you're kind of an overachiever and you just want to get it all done, that sounds nice, but but really you'd be better off breaking it into smaller chunks so that you sort of keep your mind working on it. That helps kind of just connect all of the ideas together, rather than just like getting it all done and then taking a couple days off. That's not always the best way to learn. Okay. So I'll let you guys go, and I hope to see you all on Thursday and hear from you whenever you run into any questions. And if you have some other